So we have an example here. We've got uranium being bombarded with neutrons, and that causes the uranium to become even more unstable, splitting apart in a fission reaction to produce barium and krypton, 3 neutrons and some gamma rays, some electromagnetic radiation. So what we're wanting to investigate is, or find out, is how much energy is produced in this reaction. So it might help just to have a little diagram beside, and so if we've got our uranium and our neutron, and then that's going to transmutate whatever into our barium plus krypton plus 3 neutrons. And the gamma rays, of course, have no mass, so we're not interested in that. And what we want to do is we want to look at the initial mass and the final mass, and compare those two together, and any change in mass is going to be equal to our times by the speed of light squared. Of course, it's going to be equal to our energy that is given off in this reaction. So it's important to know we need to deal with the rest masses of these nucleons, and we're only dealing with one atom of uranium, 1 neutron at the start. So you can then, if you had a sample size, you could multiply it out to the whole sample size. But as I said, we're only dealing with the rest mass. It's because when you have objects moving, anything at all moving at speed, then it gains mass according to relativity, which you can check out in other videos, which is a bit of a problem. So that's why we deal with the rest masses. It just makes the calculations much easier. So to start with, we need the mass of the uranium plus the mass of the neutron. I'm not going to work this out in a lot of detail. I'm just going to illustrate the precision that the mass measurements require, and I'm just going to essentially tell you what the mass difference is. So the initial mass of the uranium plus neutron is 390.9229. Okay, so this is a lot of significant figures, so there's a lot of precision here, and or accuracy, or depends how you take the subtle interpretations of each of those two words. And this is times 10 to the minus 27. So it's very, very small kilograms. Very, very, very tiny amount of mass. And our final mass, if we add up the mass of barium plus the mass of krypton plus the mass of 3 neutrons, that'll give us 390.5657 times 10 to the minus 27 kilograms. So very, very, very small loss. That change in mass is 0.352 times 10 to the minus 27, which would substitute in there. The speed of light is 3.00 times 10 to the 8, and you have to square that. So that's a huge, huge number. That's 9 times 10 to the 16 is that conversion factor. And that equals, when you multiply those two together, that equals the amount of energy which you get out of this, and that is 3.21 times 10 to the 11 joules, 10 to the negative 11 joules. Nearly had this way out. So a minuscule amount of mass to produce still a very small amount of energy, but it's a huge. I mean, you look at that, 10 to the minus 11 is much, much larger than 10 to the minus 27. Yeah. Now, just a note: if you're doing these calculations, I think a drawing like this can really help you with your calculations, because you can tick each one off as you add the masses, and that saves you from making little mistakes, silly mistakes in your process. But let's just do a quick little exercise that's out of interest. and let's look at the amount of energy in 1 gram if you lose 1 gram. So you would need quite a significant amount of, because remember the mass deficit was from these two was 0.3572 times 10 to the minus 27 kilograms. You would need a lot of atoms of uranium to make that a worthwhile energy loss. But remember, atoms are really small, so on a sample of uranium you can easily do that. But in any case, 1 gram, let's look at 1 gram to look at the energy, just as an interesting kind of thing to do. E equals mc squared. 1 gram is 0.001 kilograms, so it's 0.001 times by the speed of light squared, 3.00 times 10 to the 8, and that's going to be 9.00 times 10 to the 8, and 8 is 16, and minus 3 is 13 joules of energy. That's a lot of energy. That's a huge amount of energy. And I'll just show you how I got that. 3.00 times 10 to the 8 squared is 9.00 times 10 to the 16. So, and then we've got 3 decimal places that we lose. That's why it drops down to 13 from on here. So that is a ridiculous amount of energy. That's let's see, if you put it in terms of millions, you're dealing with a million, more than a million, an order of magnitude more than that. It's roughly 900,000 billion. That's a lot. That's a huge amount of energy. I couldn't give you, if you divided that over the course of, let's see, 1 hour, which is 3,600 seconds, so you divide that by 3,600 to give amount of energy per second, you're still in the order of magnitude of gigajoules, which is huge. Huge. That's like a continuous lightning strike for an hour, perhaps, as a rough estimate, and the amount of energy taken out of that from 1 gram of mass converted. So on an atomic bomb, you would I don't know how exactly the stats are. In fact, I'll pause and I'll quickly look up and see. Okay, it's very hard to find anything very direct and specific, but I've found on Wikipedia that 1 ton of TNT is equivalent to 4.2 gigajoules of energy released. So we've got clearly more than gigajoules here. This is like 9 gigajoules per second for an hour. But they talk about nuclear bombs being what was it, megatons or something. How many megatons? No, not that one. Going through, checking my web pages, sorry for the delay. Okay, 10 million tons of TNT. That was the first thermonuclear hydrogen bomb test, and that was 10 million tons of TNT, producing a huge, more than enough to demolish cities. So that's 10 million tons, that's 10 billion kilograms, and each kilogram we saw could give off, each ton, so 1 million tons of TNT is 4.2 million gigajoules. That's 4.2 million billion joules of energy, which is actually not too far off this figure. So that's the modern nuclear bombs are around about 1,000 kilograms, which means they might get around about 1 gram of actual mass converted energy during that. That's staggering, absolutely staggering, but very fascinating. Yeah, I quite like the analogy of a lightning strike extending for a period of an hour in one space and the amount of energy produced. And yeah, it's quite sobering when you think about the cost of human life in nuclear weapons. So you can see why this was a showstopper and a war stopper with Hiroshima and Nagasaki, with the nuclear weapons dropped there.